And now, Michiel, the floor is yours. You can go ahead. Thank you. I think you have already the control.
Thank you, Fernando, for this kind introduction, and welcome everyone. I see that we have about 100 participants, ranging from Senegal, I see, to the Netherlands. Welcome, Wiep, Santiago, Chile. So that's always great to use a webinar for disseminating our output of our task. So once again, welcome everyone. I'm the current operating agent of IEA PVPS Task15 on BIPV. And just zooming out a little bit, what are we going to talk about this afternoon? Already introduced by Fernando. I will give a short introduction on the IEA PVPS program and specifically Task 15. And we will go over a number of projects and different coloring strategies for BIPV. And the PVPS program, what it's all about, it started around the first and second oil crisis with the founding of the International Energy Agency. And within the International Energy Agency, there are a number of technological collaboration programs, as we call them, and PVPS is one of them, as you can read on this slide. And what we do with these 32 members from 27 countries is to enhance the international collaborative efforts which facilitate the role of photovoltaic solar energy as a cornerstone in the transition to sustainable energy systems. And what we can see here is that the global PV market is booming already for a number of years already. But if we zoom into the application of PV in the built environment, BIPV, Building Integrated Photovoltaics, we see that BIPV only has a very small market share, but and a very low estimated achieved share of the maximal theoretical BIPV potential in Europe, less than 1%. So we still have a very, very small market segment considering the whole PV market. While at the other hand, the energy consumption in the built environment is still increasing and increasing over time. So we have a huge potential of PV application in the built environment, especially integrated in buildings, but it's not being exploited at this moment. And then these are the solutions that we're a little bit afraid of. This is, of course, what we don't want to see, PV modules that are not integrated in a building and result in a positioning, a societal positioning we call not on my roof, a no-mere effect. This is not what people want. People want nicely integrated PV in their buildings. And that's what we work on in Task 15. We create an enabling framework for BIPV acceleration. And it's not about having a grand vision on BIPV or reaching grid parity, but it's really about the basic conditions for upscaling niche markets and products. Well, in a first phase that is ending now, we have focused on 5 different aspects in 5 different work packages, subtasks, as we call them. We developed a very nice database and a book with good BIPV examples. We developed business models. We worked on regulatory issues. We worked on environmental issues, and we worked on research and development activities. And this webinar is part of the last subtask that's mentioned here, the BIPV research and development activities. And if you are interested, please visit our website for more information and all the reports of these different work packages. Now we're entering a next phase of the IEA PVPS Task 15. It's phase 2. And in this phase, we're focusing as well on the technical innovation system analysis for BIPV, and what is really creating a economic conditions for BIPV acceleration. We're doing a cross-sectional analysis, develop BIPV design guidelines. We work on digitalization for BIPV, and we work on pre-normative international research on BIPV characterization methods. So if you're interested in joining or want to have more information on these work packages that we're exploring in the next phase, once again, please visit our website. And with that, yeah, very brief introduction. I'm trying to go to the next slide.
Yeah, it's up to Pierluigi now.
Okay, so with that, I'm handing over the microphone to our colleague, Luigi. Thank you.
Thank you, Michiel. Hello, everyone, and a warm welcome also from my side. It's Pierluigi Bonomo here from University of Applied Sciences of Southern Switzerland, from Lugano. So I will try to introduce you the topic of today, which concern projects and the main trends of innovation about colored BIPV. These are the main points that I will try to cover with my presentation. So I will try to give an overview on which is the status today and which are the main products generation, and also providing you some real examples of real buildings, and also pointing out a very brief hints on some challenges concerning these product technologies. So I start with a first point, since we are used to talk about BIPV as a niche market, and this is truth today, because it is, but I like to conceive building integrated photovoltaics as a part of a growing and dynamic construction sector, so as a part of a future building. And I like so to conceive this sector as a growing and potential sector for construction fields. And in this way, I believe that BIPV itself could also provide an answer to this typical question that still today, sometime we hear about solar in architecture. So sometimes still seem that aesthetics, architecture, and solar are in opposite positions. But I believe that this is not a right question, because answer today is clear, and is BIPV as a potential. I start with this building, since today we are going to discuss about colored BIPV. But a possibility for integrated photovoltaics is also to use black as a color. This is a nice example in Switzerland, where PV is colored, but is black colored. Or on the other side, colored PV is nothing really new if we take a look to some examples of some years ago, where coloring the cells was a first possibility for architecture. And this is an example. I took these pictures in Chelsea, near London, in this very nice example, where you can see solar cells with different color gradients, really ranging from greenish and yellow to also very nice brown and gold solar cells, and very nice integration with the surrounding environment. I'm pretty sure that most of you, which are PV expert, also observed on this example also some other particular features, such as very important shading on the facade. And that's why I typically use this example, because this is a possibility for BIPV, so to have real modules in non-conventional scenarios. And coming back to non-colored PV, so use of non-colored PV doesn't mean that we cannot realize solar architecture, because this is possible also with these standard components. And so use of standard colors doesn't mean to have standard architecture, like in this example, which is the Umwelt Arena near Zurich in Switzerland. You can see here some special details of this example. But that's true that with standard products, we had the first generation of integrated photovoltaics, which was connotated by also a standard language linked to the technology. And this is a clear example where the technology and the language of crystalline silicon and amorphous silicon is really recognizable and visible. So a question is, why do we need customized and colored PV? Is not standard PV enough for this sector? And you can see here our TISO PV plant installed more than 36 years ago on our rooftop of our campus. And this is a picture 36 years later, again in Lugano. Maybe most of you can recognize the brand of this fashion house, which used photovoltaic modules as part of their communication. So it's not standard PV enough? I believe that the answer can be summarized with this famous statement by Harry Ford. So the problem of standardization for architecture is quite clear, because there is not standard architecture. So the need to really fit with different architectural languages, with different aesthetics of facade, it's a need of architecture and construction sector. And that's why today we need and we have a solar revolution, which means a real change of concept and of technology. So today we can really observe evolution in the sector, since the basic solar component evolved from an element basically generating energy to an active element. This is not only linked to the component scale, but also at building level, the evolution is clear, because we are moving from a first stage of solar roof, mainly used in a southern roof, at least here in Europe, in European country. We are moving towards a new generation of fully active buildings. And you can see real what is possible today, thanks to industry and industrial evolution. So this was possible thanks clear improvement and evolution in the solar industry in the last few years. I mentioned in these few slides just some of the products today available. So I think it's quite evident, without going in details, to realize what is possible today in terms of aesthetics, in terms of construction technology. I mentioned some of the producers here, and I apologize with the rest of them for not mentioning, but today we really have a lot of possibility and chances for a solar architecture. We can say that in some applications, mainly based on glass technology, today the main limit is really the glass and no longer PV technology for BIPV. So whatever is possible with glass has been demonstrated to represent a possibility for solar architecture. And you can see here, I will slide quite briefly some examples. Here we are in Zurich. It's a building renovated by Virid and partner. And every surface that you observe here is an active photovoltaic surface. It's a conventional construction system for a building skin where the external cladding is replaced with a solar component. And again, here, other examples. I'm mainly showing Swiss examples where the cladding is completely active. So it's quite clear the change of concept in solar architecture and in the approach. So we have real buildings reality of solar buildings, where all the claddings, all facades can become active. And we have also the possibility to say that nobody today can recognize that these are solar-powered houses. So this is what is possible today. This demonstrates that we can go also beyond pilot buildings. We can adopt and implement these technologies also in ordinary building contexts. And for who of you is curious of much more detail, I can suggest you visit our website, which is supported from the Swiss Federal Office of Energy, and we are implementing with ETH and also Swiss Solar partners. You can find here much more details about these buildings. So this change of concept and of photovoltaic technology, of course, it's not free of challenges, because we open a lot of challenges, since we have multifunctional components, which of course have to produce energy, but they have to comply with a wider set of building and construction requirements. So a lot of points of innovation are under research and under examination from industries and from research institutions. I listed here some key topics on which today we are working and we are doing research. So of course, we will also see in next presentations, which is the relation between aesthetics and energy performance, and also other points. So standardization and customization, how they can dialogue, and also which is the quality and the reliability of such a products. And last but not least, which is the cost. I briefly mentioned this research that will be presented in detail by my colleague Erika Saretta later on. So just to show you that we are active on analyzing and understanding the performance of these devices. So of course, investigation is important to understand which is the effect of these aesthetic treatments on the electrical behavior, on the power production, and on the reliability of such modules. And another project again here at SUPSI, I thank my colleague Gabi Friesen for this slide. You can see here another measurement campaign that we did here at SUPSI, where we characterized some main colored and special modules. We compared the performance, and we observed some interesting results in terms of energy yield and also of thermal aspects. I put here the reference to the project, so it's not the scope of today to enter in detail of this aspect, but mostly to provide you some main reference. Another aspect, so it's also the digitalization of the process. So it's a key point of today's innovation to work on a digitized and integrated process. This is most important in case of innovative technologies. So an integrated value chain and development of softwares for designing and supporting the real stakeholders in implementing this technology is crucial and is important. And we are active also on this aspect in some ongoing European projects with our partners. Again, this technology finally also make it possible to integrate solar in sensible contexts and in protected areas. So this is also another added value of these technologies. And about cost, this is another key question, because how much does the BIPV cost is a key question for the feasibility of this kind of solar technologies. This is a quite complex question, because it's important to put in clear what the cost is referred to and which cost are we talking about. Otherwise, we risk to just mention some values of cost on square meters and so on, which are not very well contextualized. So I invite you to take a look to these two reports, and especially to the report that we developed in a BIPV Boost project, where you can find methodologies specifically developed for BIPV, and which was developed by Becquerel Institute. Just a quick comment. So just to say that about cost, it's important to highlight that cost for making active a facade or a roof, it's an extra cost in comparison to a non-active element. So the basic concept is to conceive photovoltaic as an extra cost, so which is a part of added cost for a conventional element, but it's also an active part. So everything can be calculated also on basis of the return of investment in this perspective. And these are some concrete results that we observed in some Swiss examples. So we are investigating in detail the cost breakdown and the main voices of costs for real BIPV facades and real buildings. These are some numbers. So we observed an average extra cost of 30% on facades, and we are working on that, as I mentioned, to really investigate which is the impact of these technologies and also which is the potential in the return of investment. So very quick, I ran a little bit. I hope that you will have the chance to go more in detail in the articles and reference which I put in my slides. So I can just conclude by saying that our challenge today is not just to have pilot buildings, but is to really implement BIPV as a mainstream construction product. And it's important to link innovation with a cost reduction and a real and a strategy of implementation to really ensure a growing market of these products. I will be happy to reply to any question in the dedicated session ahead. And I conclude with these slides just to say that color is a way of integration, but as I mentioned before, we have also other challenges to solve, and I hope so that every one of you will be part of this challenge, and so I wish you a nice solar design. That's all from my side.
Hello, here is Gabriele Eder from OFI in Austria, Vienna. I will take you through the second part, the technological part concerning colors of covers, coatings, printings, and films. And sorry. At the beginning, I want to show you the principal construction of a typical BIPV module based on crystalline silicon technology. I will go to the other technologies a bit later. So we have the PV active layer in the middle, and it's embedded by a polymeric encapsulant. And on the front side, we have mostly a glass cover, a front cover, or it might also be polymeric for the flexible systems, and the back cover is either glass or another panel of a construction material. And nearly all of these layers can be colored, and I want to show you now all the possibilities realized up to now. So for the color tuning of the components, we can either modify the front glass by coating, printing, or special finishing or coloring. We can color the cells or active layers by putting anti-reflective coatings on the solar silicon cells. We can have a plasmonic coating on the silicon cells. or we can use colored or semi-transparent PV active films, thin films, or OPV, as means organic photovoltaics. But there is also the possibility to use colored or patterned interlayers, which give the color, or use special solar filters. And finally, I want to show you an example for colored polymeric films, the encapsulant or the backside, which can also color the whole BIPV element. So which design possibilities do we have? We can have either uniform colors, we can have patterns or pictures, different transparency options. The surface finishing might be important, either especially in respect to glare. If we have a matte surface or a shiny surface, then the flexibility. So as shown in these two examples at the bottom, there is the possibility to have not only rigid but also flexible BIPV modules. And here we are also a bit more open for different shapes, especially also with organic PV and different materials. So for the color tuning, we have three main different implementation possibilities. So we can either do a color coding of the various components, or having a print either on a polymeric film or on the glass, or we colorize the whole material. But we always have to keep in mind that color has an impact on the efficiency of the PV module. But this is in detail, this will be explained in the last part of the webinar. So I want to start with the front glass, which surface techniques do exist to color the front glass. The one possibility is to use spectrally selective coatings. And the first one I want to show is the chromatics technology, which was developed by Swiss Inso. They use a multi-layer reflective coating on glass. It is a specific sputtering technology, and you can have different colors such as gray, terracotta, blue, or green. And if you can see at the small table I showed you here, the solar transmittance is still between 86 and 90%, so that's quite a lot. You don't lose too much by using these color codings. Then a second technology developed by Fraunhofer-ISA, the MorphoColor, is also a type of spectrally selective coating. It was inspired by the Morpho butterfly, and they use wavelength selective reflection by interference in thin films and combine it with a special surface roughness. And as you can see here, you get really very saturated colors with different individual color choice. And here you also have 90 to 93% of the original efficiency of the module compared to a black one. And what is also worth to mention, it has a very good angular color stability and reduced glare effect due to the rough surface. The other technique to modify the glass surface is printing, and either by digital printing, so before module production, ceramic colors are printed on the front glass using a 4-color inkjet printer. And by using that, you can really generate each color you want to have, and not only uniform colors, but also printing different patterns or photos on the glass is possible. You can print either on the environmental side, so we call it plane 1, so that's the outside, or on the level 2, plane 2, that's the side next to the encapsulant. And it's possible to print different patterns so that at least 50% of the glass is not printed, that enough light can pass through the glass to reach the cell and produce electricity. Another type of printing is screen printing. Here the ink is applied through a fine mesh screen onto the glass, and you can use different fabrics as as a mesh screen to generate different decorative effects. The example of this house here in Switzerland was already given by Pierluigi before, so you get a very homogeneous color effect. And in this case, you have a combination of printing on the inner side and a special satin finish on the outer side that gives you this colored matte surface, which is very nice. Then the next step, what is possible to color the active layers. Here I give you two examples of organic PV and dye-sensitized solar cells. The advantage is you are very, you have a very high freedom, flexibility and shapes and transparency and colors are related to, but with these we call it third generation technologies, still is that the long-term stability is not very good up to now, and also the efficiency is not very high. So these are still two very important topics where a lot of research has to be done. With thin film technologies, you can also reach a certain degree of transparency. Here I give you three examples for different thin film technologies. So here, in the first example, the amorphous silicon layer is partially removed by a laser treatment, and then you get this nice transparency. So you can have it in the windows and facades, and it gives you a shading effect, but you have an active facade which is producing electricity as well. Also, the second example with cadmium telluride, and third with CIGS have the same effect. You have a high degree of transparency, but you lose, of course, a certain amount of electricity production. Transparency with the standard crystalline silicon technology can only be achieved by a special cell arrangement. So if you increase the distance between the silicon cells, because the silicon, of course, is not transmittive at all, then you can have a shading effect plus having good lighting in the room beneath. Or you use laser cutting and have special holes in your silicon cells, but it's possible to control the light increase into your house by using this technology. So then the other way to color silicon cells, crystalline silicon cells, is to have anti-reflective coating on the cell with a special thickness. So nearly all the crystalline silicon cells have an anti-reflective coating to decrease the high reflectance values. Usually the optimized coating has a blue color, which you all know from the mono and polycrystalline cells. But if you change the thickness of the film, then you can achieve a special color effect. The other way to color the crystalline silicon cells is plasmonic coating, where you have little small metallic nanoparticles on the surface, and they give the color to your cells. The nice thing with this system is that you have a very high insensitivity to the angle of observation. Then the next possibility is to use colored or patterned interlayers or special solar filters. With this technology, CSCM, the Center of Swiss Electronic and Microtechnique, had two projects showing really white BIPV products. They used a very special scattering and reflection filter on the surface of the front glass cover, but at the expense of efficiency reduction of nearly 40%. And Caleo Solar realized a technological solution with integrating high definition images into the solar panels. And the picture here on the right hand side, you see that you get really then a very nice effect of the picture. So the last example I want to oh, I'm afraid I ran out of time. I can't use the, so I think it's Erica's time.
You can probably take your time to finalize your pending slides.
I just want to. I have only 2 slides left with colored polymeric films, where here in this case the encapsulant beneath the solar, the thin film is colored, so it does not go on the expense of the efficiency. And finally, this is the bridge to the next talk, is that you should keep in mind that mainly when you put a lot of effort in color and transparency, then of course it's always this field of tension that you lose electrical performance. Thank you very much.
Okay, good afternoon. I think that now you should be able to see the first slide of the last presentation of today's webinar. My name is Erika Saretta. I am a research assistant of the Innovative Building Scheme team. I work with Pierluigi at the University of Applied Science of Southern Switzerland. And my presentation today concerns the results of some experimental campaigns on colored BIPV modules. The first question is, why should we care about colored BIPV modules when for years we put a lot of efforts for increasing PV modules efficiency? And to try to answer this question, I think that we have to consider the need today of having also BIPV facades beyond roofs. This is due to the fact that we need energy production from morning to afternoon to increase the building self-consumption. And thanks to the different orientations of BIPV facades, it is possible to achieve this goal. And moreover, BIPV facades are needed also because building facades have larger surfaces in comparison to roofs, especially for multi-story buildings. And the use of also these surfaces can help in achieving the energy balance of a building. And moreover, the facades is more than a wall. It is also an expression of an architectural language, because when a building owner wants to realize a building, she or he has an idea of the aesthetical goal that she or he wants to achieve. And facades are also architectural language. And this is the reason why today in the market there are colored BIPV modules that are emerging and spreading all around the world. And as we have already heard from previous presentation, there are different customization options for realizing colored BIPV modules. And some of them are the type of glass, the type of colors, the different techniques for printing colors on glass. And also there is the possibility to choose the position of the color. So we can apply color on position 1, meaning on the outer side of the front glass, or in position 2, in the inner side of the front glass. And this involves that the efficiency of the PV cell of the module can decrease due to the additional layer, colored layer put in the module. And this led us to the question, how do glass customization options affect the electrothermal behavior of BIPV? And this is the reason why today I'm going to present you the results of the first experimental campaign on colored BIPV modules realized with mineral coating, and the second campaign on colored BIPV modules realized with digital glass printing. So for the first experimental campaign, I will present the results of the electrothermal characterization on monochromatic BIPV modules. And in particular, we characterized the modules both indoor and outdoor by the power measurements on the single prototypes and the power and temperature measurements on the single prototypes in outdoor condition. So thanks to the collaboration with Swiss BIPV module manufacturers, we obtained some small prototypes, glass modules realized with mono crystalline cells connected in series. And we asked for different design options for the front glass. So we had different prototypes with different glass type, so float glass or satin finish glass. We applied color in position 1 and position 2, and then we asked for different color types that have been applied with a 10% of transparency. And here you can see some pictures of some of the prototypes that we work with. In particular, you can see here the results of the power measurements that we perform at the standard test condition. And you can see that for each color, we have the prototypes with satin finish glass with color applied in position 2. We have prototype with float glass and color applied both on position 2 and position 1. What is important to note from these graphs is that the glass type doesn't affect significantly the power output, as you can see here. Indeed, the maximum difference is in the amount of 3.3% for the dark gray, and the minimum is in the amount of 0.53% for the green modules. And moreover, it is interesting to note that there is no evidence of a difference in efficiency when the color is applied on position 1 or position 2. What affects mainly the power output instead is the color type. As we can see here, where the same results are displayed depending on the glass type, we have that the maximum differences in terms of power output is in the amount of 17% when we compared the dark gray with the reference model. And also, it is nice to see that the blue modules is the one that have good performances. However, another important aspect to investigate was the possible temperature effect to the application of the color on the modules. Indeed, when the temperature of the module increases, the power output decreases. So to investigate such an aspect, we set up an outdoor stand where we installed some of these prototypes as facade elements, so in the vertical position, and we equipped them with a special MPPT for monitoring these small modules. And from the results, it arises that the possible temperature effect due to the application of color on the modules is not so high and significant. Indeed, the temperature range among the different color modules is in the amount of 2 degrees. So that we can say that different power output is not significantly affected by the operating temperature, but it is mainly influenced by the color type. It is not due to the temperature, but due to the behavior of the radiation that hit the front glass and then the PV cells. So these are the same results, but more in detail. So from the evaluation of 3 different moments during the day, during this clear day, we have the detail of the different temperatures that we monitor among modules. And so from this section, it arises that The main influencing parameter on the electrothermal behavior is the color type, even if the operating temperature seems to not affect significantly the power output, also because in this case, for these prototypes, we applied a low percentage of color, even if this color can be seen on the modules. So the cells from the far distance cannot be seen. So what I have presented so far is related to monochromatic BIPV modules, but now I want to discuss also the topic of designing multichromatic BIPV modules, since we want to make architects free to develop their facades, and also we want to enable them to use different colors if they want. And for this reason, we developed this methodology that consists of 4 steps. So we have an indoor characterization, where we calculated theoretically the mismatch for different pairs of prototypes combined in series by evaluating the IV curves from indoor test. And we verified the results with the physically combined prototypes in our lab. Similarly, for outdoor characterization, we calculated the mismatch on single IV curves from outdoor monitoring, and then we measure the mismatch on physically combined prototypes. Here this is an example of how we calculated the maximum power for the prototypes combined in series by evaluating the IV curves. So we merged the IV curves obtained from the power measurement test, and we considered the maximum power point to calculate the maximum power, so the yellow area. And the results in terms of power output for some combination are shown here. You can see on the left the 2 reference modules, and the difference is in terms of reduction of power output for different combinations. And we have that the best combination, both in terms of efficiency and in terms of contrast of colors, is the blue and light gray combination, whereas the light gray and terracotta perform worst, even if the difference is in the amount of 6.4%. So we evaluated also with our test facilities the power output of combined prototypes, and these are the results. So in green we have the calculated values, and in blue we have the measured values. So you can see that the errors are very, very low, meaning that this combination and this method is accurate to estimate a possible combination of different colors of modules. But we were also interested in applying this method for the outdoor conditions. So in this case, in this graph, you can see the values of the power output for the different combination of colored modules at indoor condition in green, but also in red, orange, and yellow. You can see the calculated value of power for different combination of modules when they are outdoor. So we merged the IV curves from outdoor monitoring, and we calculated the mismatch and the power output. And you can see that the power reduction in this case is significantly higher, even if the trend is more or less the same. Then, to evaluate this calculation, we connected in series different combination of modules, and we measured the real value that is lower than the one calculated, and we have huge differences. So in conclusion, we can say that this calculation method for a standard test condition is very accurate, but the same calculation method for outdoor condition has some errors due to the fact that there are some conditions, real operating conditions that affect the behavior of these multichromatic modules. So this is a still open research field that still needs to be investigated. But for the monochromatic modules, in this experimental campaign, we can say that the main influencing parameter is the color type. And moreover, even if you can see the color on the modules with this low percentage of color used, the operating temperature is not significantly affected. So the electrothermal behavior of such modules is good. Okay, so the last experimental campaign that I'm going to present is about color BIPV modules realized with digital printing. And we carried out these campaigns in the framework of the European project SmartFlex that was aimed at demonstrating the flexible manufacturing of multifunctional and customizable BIPV glass elements at the industrial scale and for ordinary buildings. And one of the goals was to try to customize BIPV modules in terms of dimensions, layers, shapes, and appearance. And for this reason, we investigated different BIPV colored prototypes realized with digital printing and with different customization options. So we changed the color, we evaluated the change in the thickness of the dots. We change the printing degree, as you can see here, from 100% to 0% to have a reference. And we change also the position of the application of the color from position 1 or position 2. In particular, we measure the power at standard test condition and the spectral responsivity. Also, we measured the power for different irradiance values, and we carried out the outdoor monitoring of power and temperature of some colored modules. From the results, you can see that in terms of power output, we have a range of reduction in comparison to a transparent model that run from 9% to 33% for the worst case, so the black opaque model. But for instance, the white model, the green have good, still good performances and good power. We can say that the dot positioning in this case doesn't affect the power output, as you can see here from the graph on the right. And instead, what affects the power output is the opacity of the dots, meaning the thickness of the dots that is applied on the glass. Meaning that if you have more color on the dot, the radiation cannot pass totally through the dots, so cannot hit the cells and cannot be converted into electricity. This means that it is a trade-off of selecting the correct amount of color to be applied in order to make it visible, but also in order to make the light, to let the light pass through the dots, and so to be converted into electricity. We assess also the spectral responsivity of some colored modules. And as you can see here, we have that the black module absorbs the radiation with wavelengths corresponding to the visible and also the infrared radiation, whereas the module with green dots absorb the light at the wavelengths corresponding to the blue and red colors, and the module with white dots reflects and transmits the light over the complete spectrum. And this can be seen also here in the outdoor monitoring of these modules, because as you can see here, the power output of the black modules is the lowest one, due to the fact that the light is absorbed, and this absorption is converted also in heat, and this increases the operating temperature of the modules, and the power is negatively affected. Whereas, for instance, for the white model, we have that the operating temperature is lower because the radiation is reflected, even if we have still quite good power output. So the results of this experimental campaign confirms again that the color type is the main influencing parameter on the efficiency of modules. Depending on the color type, we have different power differences. We have observed differences from 9% to 35% for the black opaque modules. And other influencing factors are the dot density, but also the opacity of the color, so the thickness of the dots of the colors. That affects the amount of radiation that passes through the color layer and also affect the visual perception of the color. So to conclude, we have now, we are aware of the customization aspects and how they affect the real behavior of colored modules. And these kind of products are always a trade-off among efficiency and aesthetics. So there is always the chance to set up the right combination and the right setup for having a good product, not only in terms of aesthetics, but also in terms of efficiency. So to conclude, I want to mention the projects that allows us to investigate this topic and also the module manufacturers. And I want also to thank you for the attention.